This is my Physics 2112, Lab 5 on Faraday's Law. The main goal of this lab was to study the magnetic currents by analyzing a bar magnet traveling through an aluminum tube and comparing it to a computational model that we developed through GlowScript. Some important concepts we're going to need to know is Faraday's law, Biot-Savart law, and Newton's second and third laws. Faraday's law says a change in magnetic field through a loop induces a voltage that is proportional to the negative change in the magnetic flux over the change in time. Biot-Savart's law says that a steady current produces a magnetic field around it with strength depending on distance and current. Then Newton's and second laws, for the sake of time, I'm going to not explain because we've been using them for the past two courses. Some assumptions we made in this lab were that air resistance was negligible, the bar magnet acts as a magnetic dipole, and the only forces acting on the system are the force of gravity and the magnetic force from the magnet and the induced currents in the copper or in the aluminum tube. As you can see on the right, we have a small diagram that I found online that indicates how an induced dipole reacts with a magnet falling through a conducting tube. In our case, it was aluminum, and in this case, it is a copper tube. As we can see, the sketched lines indicate the magnetic field as we drop the magnet through the tube, and the induced current in the tube as the yellow lines. During our experiment, we found the average fall time of the magnet through the tube to be 1.22 seconds. The tube's length was 0.3 meters. The inner radius of the tube was 0.025 meters, and the outer radius of the tube was 0.03 meters. This leaves the thickness of the tube to be 0.005 meters. The mass of the magnet was 0.025 kilograms. These will be important in the glow script we show in the next slide. So here I have a couple clips or snippets of my code. In the top center is where I inputted all of my, I left out all the spots where I inputted my data, and this is where the data carried through. This is the meat and potatoes of the code. And on the left, you can see the graph of my, the graph that was produced. This is my computational model. The first portion of the graph was the magnet before the current was induced. And as you can see, the velocity of the magnet decreases in speed, and at about 0.15 seconds, it levels off into a constant rate. This is when the magnet is slowed to a terminal velocity when the force of gravity is equal to the magnetic force by the induced current. And then at about 0.8 meters or 0.8 seconds, we see that the magnet decreases again. And that's where it's exiting the tube. Questions and discussions. What would happen if we flipped the magnet? Nothing. The induced current would be equal, just in the opposite direction. Change in time, computational versus experimentally. The computational was slightly shorter due to human error and air resistance, because neither one of those things can be accounted for. How would the dynamics change if the tube's resistivity was close to zero? It would increase the induced current due to Ohm's law, where volts equals current times resistance, and slow the magnet more. What if there were slots cut into the tube? There would be less rings, magnetic rings, or I guess current rings, causing the magnet to fall faster. Thank you so much.